This is a presentation on sets. A set is a collection or list of objects, quantities or numbers with specified properties. A set is a collection or list of objects, quantities or numbers with specified properties. A set is usually denoted by capital letters such as A, B, P, Q, X, and Y. The objects that makes up the set are called elements. The objects that makes up the set are called elements of the set by a description enclosed in braces. A set is usually denoted by capital letters such as A, B, P, Q, X, and Y as shown. The objects that makes up the set are called elements of the set by a description enclosed in braces as shown. Now, when we consider the set Q, the members of the set Q or the elements of the set Q are 2, 4, 6, 8, and 10. These are the members or the elements of the set Q. So the members of the set Q are called elements. So the elements of the set Q are 2, 4, 6, 8, and 10. Now, when we look at the set Q, we can see that 4 is a member of the set Q. That is, 4 is a member of the set Q. And in set operations, we write 4 belongs to Q. We write 4 belongs to Q, where this symbol is used to denote the clause belongs to, or is a member of, or is an element of. So because 4 is a member of the set Q, then we say that 4 belongs to Q, or 4 is an element of Q, or 4 is a member of Q. Now when we consider the same set Q, the elements are 2, 4, 6, 8, and 10. So we can see that 5 does not belong to Q. 5 does not belong to Q. So this symbol is used to denote the clause does not belongs to. Does not belongs to. So we can see that 5 does not belong to Q because 5 is not one of the elements of the set Q. So we say 5 does not belong to Q. Now let's look at some definitions. An odd number is a number which cannot be divided exactly by 2. An odd number is a number which cannot be divided exactly by 2. When we say an odd number is a number which cannot be divided exactly by 2, then we mean that when we divide an odd number by 2, there is a remainder. When we divide an odd number by 2, there is a remainder. Now these are examples of an odd number. We have -5, -3, -1, 1, 3, and 5. Now, these are the examples of an odd number. When we divide -5 by 2, the answer is -2.5. Because the answer is a decimal, it means that there is a remainder. When we divide -3 by 2, we have -1.5. That means there is a remainder. That makes -3 an odd number. -1 divided by 2 equals -0.5. The answer is a decimal. It means that -1 is an odd number. Similarly, 1 divided by 2 equals 0.5. 3 divided by 2 equals 1.5. And 5 divided by 2 equals 2.5. The answers are all decimals, meaning that when we divide the numbers by 2, there is always a remainder. And that's why they are odd numbers. So odd numbers cannot be divided by 2 exactly. Now, let's look at an even number. An even number is a number leaving no remainder when divided by 2. An even number is a number leaving no remainder when divided by 2. And these are examples of an even number. We have -6, -4, -2, 0, 2, 4, 6. These are examples of an even number. These are examples of an even number. Now, when we divide an even number by 2, it leaves no remainder. Take note, it leaves no remainder. Now, these are examples of an even number. We have -6, -4, -2, 0, 2, 4, and 6. When we divide minus 6 by 2, the answer is minus 3. The remainder is 0. That is why minus 6 is an even number. When we divide minus 4 by 2, the answer is minus 2. No remainder. When we divide minus 2 by 2, we have minus 1. When we divide 0 by 2, we have 0. 2 divided by 2 equals 1. 4 divided by 2 equals 2. And 6 divided by 2 equals 3. So when we divide even numbers by 2, it leaves no remainder. It leaves no remainder. And that is shown by the illustration we have here. Now let's look at factors of a number. Factors of a number. Factors of a number are elements that can divide a number leaving no remainder. Factors of a number are elements that can divide the number leaving no remainder. So when we consider the number 12, factors of the number 12 are 1, 2, 3, 4, 6, and 12. So these are numbers that can divide 12 leaving no remainder. That is when we divide 12 by these numbers. When we divide 12 by the factors of 12, it leaves no remainder. Let's look at the illustration. Now, the factors of the number 12 are 1, 2, 3, 4, 6, and 12. When we divide 12 by 1, the answer is 12. The remainder is 0. When we divide 12 by 2, the answer is 6. No remainder. When we divide 12 by 3, the answer is 4, leaving no remainder. When we divide 12 by 4, the answer is 3. 12 divided by 6 equals 2. And 12 divided by 12 equals 1. So when we divide the number 12 by the factors, we can see that we have whole numbers. It leaves no remainder. We have 12, we have 6, 4, 3, 2, and 1. So when we divide 12 by the factors of 12, it leaves no remainder. It leaves no remainder. Now let's look at a prime number. A prime number is any positive number that has two factors, itself and 1. A prime number is any positive number that has two factors, itself and 1. A prime number is any positive number that has two factors, itself and 1. Example of prime numbers are 2, 3, 5, 7, 11, 13, 17, etc. Now, considering these prime numbers, we can see that 2 is a prime number, even though it's an even number. 2 is also a prime number. Why? Because 2 has two factors, itself and 1. 3 has two factors, itself and 1. 5 has two factors, itself and 1. 7 has two factors, itself and 1. So prime number is a number that has two factors, itself and 1. Prime number is a number that has two factors, itself and 1. Now multiple of a number. Multiple of a number. Multiple of a number x refers to any number formed when x is multiplied by any integer. Example, multiples of 3 are 3, 6, 9, 12, 15, etc. So the multiples of 3 are 3, 6, 9, 12, 15, etc. Now when we multiply the number 3 by 1, we have 3. When we multiply the number 3 by 2, we have 6. When we multiply the number 3 by 3, we have 9. When we multiply the number 3 by 4, we have 12. And when we multiply the number 3 by 5, we have 15. So when we multiply the number 3 also by 6, we also have 18. Now the multiples of 3 are 3, 6, 9, 12, 15, etc. A set P is said to be a subset of the set Q if all the elements of P belongs to the set Q. I repeat, a set P is said to be a subset of the set Q if all the elements of P belongs to the set Q. The symbol, that is this symbol, is used to denote the phrase subset of. That is the symbol used to denote the phrase subset of. Subset of. Now, let's look at this example. Considering the set P, the elements are 2, 5, and 8. And considering also the set Q, the elements of the set Q are 1, 2, 3, 5, 7, and 8. Now we can see that the members of the set P can all be found in the set Q. That is 2, 5, 8 can all be found in the set Q. 2, 5, 8. So we can write that P is a subset of Q. Why is P a subset of Q? This is because all the members or all the elements of the set P can all be found in the set Q. That is 2, 5, 8 can be found in the set Q. 2, 5, 8. So we say P is a subset of Q. Now, with the set A equals 3, 6 and the set B equals 1, 4, 5, and 8, we can see that the element of the set A cannot be found in the element of the set B. I repeat, the element of the set A cannot be found in the set B. So we say that A is not a subset of B. A is not a subset of B. A is not a subset of B. And that is the symbol we use to denote it's not a subset. It's not a subset. The universal set. The universal set is the set of all objects under discussion. The universal set is the set of all objects under discussion. The universal set is the set of all objects under discussion. We use the symbol U to denote the universal set. Example, if U equals even numbers between 2 and 20, that means that the universal set will be 4, 6, 8, 10, 12, 14, 16, and 18. U equals even numbers between 2 and 20. Because they are even numbers between 2 and 20, it means that 2 and 20 themselves are not inclusive. And so it's between 2 and 20. So the universal set U equals 4, 6, 8, 10, 12, 14, 16, and 18. An empty set. A set which contains no element is called an empty or null set. A set which contains no element is called an empty or null set. It is usually denoted by, these are the symbols we use to denote an empty set or a null set. These are the symbols we use to denote an empty set or a null set. The complement of a set. The complement of a set. The complement of a set, say A, is defined as the set of all elements of the universal set U. The complement of a set, say A, is defined as the set of all elements of the universal set U, which are not elements of A. What do we mean by this? Let's look at this illustration so you understand what we mean by a complement of a set. Now, considering the set A, the elements are 1, 3, 5. If A is a subset of the universal set, U equals 1, 2, 3, 4, 5, 7. The elements of the set A are 1, 3, and 5. And the elements of the set A can all be found in the universal set. That is 1, 3, and 5. However, we can see that there are some elements that belong to the universal set U, but does not belong to A. And the elements are 2, 4, and 7. 2, 4, and 7. These are the elements that belong to the universal set U, but does not belong to the set A. So we say that the complement of A, written as A complement or A prime, is given by A complement equals 2, 4, 7. that is 2, 4, 7. These are elements that belong to the universal set U, but does not belong to the set A. That is what we mean by the complement of A. That is what we mean by the complement of A. Now we look at operation on set. Operation on set. Operation on set. Intersection of sets. Intersection of sets. The intersection of two sets, A and B, is defined as a set of all elements that belongs to both A and B. The intersection of two sets, A and B, is defined as a set of all elements that belongs to both A and B. Now, example, when you consider these two sets, elements of the set A are 1, 2, 3, 4, 5, and 8. And the elements of the set B are 2, 4, 6, 8, and 10. Now we can see that there are particular elements which belongs to both the set A and the set B. And those elements are 2, 4, 8. Because 2, 4, 8 can be found among the elements of the set A, and 2, 4, 8 can also be found among the elements of the set B. So because 2, 4, 8 belongs to both the set A and the set B, then we say that A intersection B equals 2, 4, 8. That is elements that belongs to both A and B. Element that belongs to both the set A and the set B. That is what we mean by intersection of sets. Now we have union of sets. Union of sets. The union of two sets, A and B, is defined as the set of all elements. The union of two sets, A and B, is defined as the set of all elements that belongs to either A or B or both. That belongs to either A or B or both. That belongs to either A or B or both. Now let's look at the illustration. Considering this example, the elements of the set A are 1, 2, 3, and 4. And the elements of the set B are 2, 4, 6, and 8. Now when we say A union B, it means that we are to combine the element of the set A and the element of the set B. But take note, for union of sets, repetition is ignored. What do I mean by repetition is ignored? When we look at the element of the set A, we have an element 2. And that same element 2 can also be found in the set B. So when we are writing the union of A and B, we write only one. We don't repeat the number 2. And the same thing applies to 4. So A union B equals 1, 2, 3, 4, 6, and 8. That is 1, 2, 3, 4, 6, and 8. 2 does not repeat itself in the union. And 4 also does not repeat itself in the union. Normally, it's done in ascending order. That is from the least to the highest. So with the union of sets, we only combine the two sets in ascending order from the least to the highest. But take note, repetition is ignored. Now let's look at some solved problems. Given the set A equals 2, 3, 4, 5, and 7. The elements of the set A are 2, 3, 4, 5, and 7. And the elements of the set B are 2, 3, 4, 7, 10, and 19. We are given the universal set, and these are the elements 2, 3, 4, 5, 7, 10, 13, 19, and 37. Now we have to list the elements of A complement intersection B. A complement intersection B or complement. Now let's look at the solution. From the question, we were given the set A and the set B and the universal set. And the elements of the set A are 2, 3, 4, 5, and 7. And the elements of the set B are 2, 3, 4, 7, 10, and 19. Elements of the set U are 2, 3, 4, 5, 7, 10, 13, 19, and 37. Please, when you are solving a problem, don't circle the answers as shown. Don't circle the element as shown. Don't circle the element as shown. This is to help you to understand how the problem is being solved. Now, we are asked to find A complement intersection B. A complement intersection B. Now, when we consider the elements of the set A, we have 2, 3, 4, 5, and 7. And this is the universal set. So A complement are elements that belong to the universal set, but does not belong to the element of the set A. That is what we mean by A complement. Now, when we look at the elements of the set A, we have 2, 3, 4, 5, and 7. And these are the elements that are circled in the universal set. 2, 3, 4, 5, and 7. However, there are some elements in U which cannot be found in A. And the elements are 10, 13, 19, and 37. And so A complement is equal to 10, 13, 19, and 37. These are the elements that can be found in the universal set but cannot be found in the set A. That is what we mean by the complement of A. So A complement equals 10, 13, 19, and 37. Now you have to find A complement intersection B. A complement intersection B. A complement intersection B. Now we have A complement, and the set of A complement are, the elements are 10, 13, 19, and 37. And B has been given from the question, that is 2, 3, 4, 7, 10, and 19. So A complement intersection B means that we are to search for elements that belongs to A complement and also belongs to B. And we can see that the elements are 10 and 19 because 10, 19 belongs to the set B and 10, 19 also belongs to the set A complement. And therefore A complement intersection B is equal to 10, 19. Now, we were given A in the question, we are also given B and the universal set. Now, A complement intersection B complement. From A complement intersection B give us 10, 19. 10, 19. So, A complement intersection B or complement means we are to search for elements that belongs to the universal set but does not belong to A complement intersection B, that is 10, 19. And when we look at the universal set, 10, 19 are elements that belongs to A complement intersection B. So all the other elements that does not belong to A complement intersection B are the members of the set A complement intersection B or complement. So we have 2, 3, 4, 5, 7, 13, and 37. And that is how come A complement intersection B complement is equal to 2, 3, 4, 5, 7, 13, and 37. That is elements that belong to the universal set U but does not belong to A complement intersection B, that is 10, 19. And the elements are 2, 3, 4, 5, 7, 13, and 37. Now, let's consider a Venn diagram. Venn diagram. A Venn diagram is a diagram that shows all possible logical relations between a finite collection of different sets. Between a finite collection of different sets. Now we consider a two-set problem. Number of U is the universal set. Let's assume that this number of U represents the total number of students in a particular school or a particular class. And let the number of A represent the number of students who read Greek. And let number of B be the number of students who read biology. Now we have A